So now, after our first step through the Alpine Himalayan belt across the Western Alps, construction of the orogenic wedge, now we're going to move to Himalaya Tibet, which will illustrate construction of an orogenic plateau. So if I summarize, close to the axis of rotation of the plate that controlled opening of the Central Atlantic and then South Atlantic. Well, the Western Alp is a narrow orogeny belt with a triangular shape, wedge shape. And it's constructed by burial and exhumation of units along the plate boundary, coastal units, oceanic and continental, that were decoupled from the downgoing slab. That's what we've shown yesterday. So what happens to the Himalaya Tibet? Do we find similar type of record, geological record? Well, obviously the structure looks different. It's a much wider belt with a higher topography at the front and then the plateau at the rear. And we related that the width of the belt to the position far from the rotation axis. So how does it look like? And one of the questions we're going to ask is, where does this material come from? Material that constitutes the thick crust beneath Tibet. Where does it go? You know, what is its history? Although we don't see it very well, because it's underneath the plateau. So in terms of previous work, rapidly, always the same guy, Argan, proposed one century ago that the Tibet plateau was underlain by a zone of thick crust, thick Indian crust, that was down-thrusted below the Eurasian crust, with the Himalayas forming the front of that zone of thick crust. So we just move several tens of years, and then we have the homogeneous lithospheric thickening model, which was proposed after the indentation, the punch model, rigid indentation of India into Eurasia. And here the idea was that after collision, thickening would be homogeneous at the lithospheric scale. So the crust and the mantle lithosphere, the lithospheric mantle, will thicken homogeneously. But in the same years, some other authors said, okay, maybe you have thickening of the crust, but at the same time, the lithospheric mantle might still be going into subduction. So that was the first idea that the crust and the lithospheric mantle could be decoupled. So this leads to these issues that we're going to address: how we can relate plate kinematics and orogenic evolution, which type of rocks, metamorphic rocks, are generated and how are they exhumed during orogenic evolution, and how does it relate to topography and tectonics. So I just remind you about this indentation model, rigid in India, punching soft Eurasia with extrusion of blocks, and that provided a nice way to correlate plate kinematics with continental deformation. But the main assumption here is that India is rigid and Eurasia is weak. So how do we justify that? And that deformation is very localized along lithospheric, coastal to lithospheric shear zones that should be vertical. What this doesn't account for is the coastal thickening and topography, which are first order features here. So that's obviously something is missing in that model. But still, afterwards, researchers kept nourishing this model, looking at current day displacement of point with a GPS, a global positioning system network, with stations put in different places that allow to reconstruct the displacement vector. And again, this is the same as when you look at satellite images. These are mostly measured by satellite. A satellite, they look at the Earth from the top. So it's difficult to measure vertical motion. It's more adapted to measure horizontal motion. But we see here the vertical motion indirectly. So, but let's first analyze this image. So that's the reference frame. That's 20 millimeter per year, so 2 centimeters per year. The Indian plate is moving like this. You might not see it, but there is an uncertainty circle around that, or ellipse around that vector. So that's the motion of India relative to Eurasia fixed. It's always relative motion. And you see that here, across the topographic front, the vector changes its norm, right? It goes from this size to this size. What does that mean? Slow down, yes. But if, okay, that's a good point, in terms of vector, it slows down. But where does the material go if it slows down? So that in between this point and this point, it's not just a matter of velocity, it's a matter of mass conservation. So if there's a point here, and I'm moving faster than he's moving, what's happening in the material of the in between? Compression, that's the tectonics word. Huh? So that's compression, meaning, and what you have in mind? Thickening. That's it. So horizontal shortening in terms of deformation, vertical thickening, compression. I accept it. So you see indirectly vertical motion here. And crosstal thickening should be then followed by isostasy, topography. So we have here a good correlation between the displacement field, kinematics, deformation, and topography. But then what happens? You see the vectors change also orientation, and they move from north-south to east-west. So maybe I should have started with that. At first order, you see a change in orientation of the vectors from north-south to east-west. What do you think? Compared to this model, which is actually here. Does that fit that model? From north-south to east-west. Yeah? At first order, it looks like it fits, right? You have a change in displacement of material from north-south to east-west. So a transfer of displacement from north-south to east-west. So at first order, this current day displacement field looks like it matches the indentation model. And then, if we analyze further, then we see that that's not enough. There is shortening here that is accommodated by thickening, and not only by extrusion. The material not only goes north-south, east-west, it also goes on the vertical dimension. And it's more compelling when you look at here. On the eastern side of the Tibet plateau, you have the norm of the vector is here small and then it's big again. What is happening here to the material? It corresponds to the topographic front on eastern Tibet. Goes from high to low. So if a point here is moving faster than me, what's happening to the material in between on the horizontal scale? stretching, horizontal stretching. And what happens in the vertical dimension? Thinning. So in other words, it looks like a wave here. You have thickening here and then shortening here. So this idea of rigid blocks is not matching that field. At first order, if you just look at the orientation, okay, north, south, east, west, that works. But there's more than that. It's north, south, thickening, thinning. So we'll come back to that. Just a quick view of what this guy, Taponnier, he recently died. He was a very famous French tectonics geodynamics guy, and his work was very influential. And so influential that in the last years, he went, I think, too fast. Again, this idea was brilliant. It made a very much stimulation in the community. But when you look at this picture, so there he sort of accounted for crustal thickening and lithospheric thickening. Crust is in purple and the lithosphere is in green. So he changed it a bit from his view only from the horizontal plane. Then he also added magmatism. All the red blobs are plutonic rocks that he associates here with subduction zones. So it's mostly arc magmatism. And how does he explain the Tibet plateau from this sketch? Maybe I should have asked you that question. How can we explain a plateau? What limits the thickness, the topography of mountains? And what limits, if we say, can we turn this question somehow differently? What limits the altitude of a mountain, do you think? What are the processes that we have in store? Sorry?
So the force is major contributor to elevation, because higher the force is, more will be the elevation of the...
Which forces?
The collisional...
Okay, the plate tectonic force. Huh? Okay, a plate tectonic force. So if you take a shovel and with sand and you push the shovel, is there a limit to the size of the sand pile? Gravity. So there is at some point a balance between gravity and plate tectonics. That's one solution. Lithospheric delamination might also promote high topography, but will that limit topography? See, it's slightly different. What about erosion? Erosion might also flatten the mountains. Gravitational collapse, but that's, yes, that's somehow the idea of having gravity competing with plate tectonics forces. Okay, we're there yet. But is it what is implied in this reconstruction here? What do we see? One subduction here, another one here with a question mark. Some question here. Another one here, another one here. And for each subduction, a wedge. The implication here is that in this model, the plateau is explained by juxtaposition of orogenic wedges. There's one wedge, and then another one, and another one, each one related to a subduction. And that was the idea that each suture would correspond to one plate closure, right? So one suture, one plate. 1, 2, 3, 4, 5 sutures, 5 plates. 1, 2, 3, 4, 5. And what I find also compelling in that figure, in blue here, the blue lines are meant to represent the seismic tomographic image of the lithosphere at the time he was publishing this paper. So basically what does he show here? Blue line that are supposed to represent the lithospheric structure. Do you think the green line follow the blue lines? No. This guy is that's just human histories of research. This guy was at the Institut de Physique du Globe, Institute for Physics of the Globe. But he was mostly a geologist. And he told just his geophysics guys, okay, your data, I don't care about it. I do what I want. That's what I read in that picture. Okay, so now we're gonna, yep. Sorry, because the air conditioning, I don't hear.
Could you explain once more this the turning of the vector?
Yes.
Could you explain that one?
Again? Huh? So just explain, or I mean, just present the data. The data show that the vector direction changes from north-south to east-west, but at the same time, the norm of that vector diminishes where it crosses the topographic front, which means that material has been shortened in the horizontal direction and thickened in the vertical one. But there is also some motion lateral. And across the other topographic front here, the norm of the vectors changes and increases. That means that in between here and there, the material has been stretched and in vertical direction, thinned, shortened.
Why is it turning?
I would see that. That's the last slide of the day. So we move from that idea of punching several times with extrusion laterally with another model that I'm going to develop with data analysis for the next hour, and then we have the conclusion. I can give you the conclusion right now if you want. But I think it's better if I build a demonstration. By the way, I think also through these lectures, you should feel that science is about demonstration, rational demonstration. So we might have different interpretations, but we rely on the same data. It's not always easy to decide what is really data and what is interpretation. But we try to be as objective as possible. And in my demonstration, I build a reasoning based on rationality and analysis of data. And what you learn when you're bachelor's is to acquire the methodology in order to acquire the data, and the knowledge, the definitions, and then moving to master and doctoral programs, then you learn how to develop the technology, use the technology to demonstrate and answer questions scientifically. So the demonstration is a big part of it. It's not just giving data, right? So let's just go across the Himalaya, Tibet, go through a few slides, and then we'll proceed with our demonstration. So in terms of topographic and geologic unit, you have the main central thrust, so there's the frontal thrust, the Gange plane, the Himalaya belt, and then the Tsangpo suture, in this Tsangpo suture. And we're going to also see some place at some point Ladakh in my presentation and in the one of Malika. And then we go into the plateau, the Tibet plateau. But in the Tibet plateau, there are several units that are separated by suture zones that are put in green here, that delimit crustal blocks, Lhasa block, Kyongtong block, Tsongpong Ganze, Kaidam block. And in between there is a zone of depression, the Tarim Basin. You also notice here alignment of lakes that corresponds to rifts, zones of horizontal stretching, but east-west. And that's somehow consistent with that, right? Okay, so that's the view with the blocks, Lhasa, Kyongton, Tsongpong Ganse, and Kaidam. And that's a similar view, that's 2000, Yin and Harrison 2000. Similar view than the one proposed by Taponnier, with juxtaposition of several wedges, each of them associated with closure of one ocean with one subduction. And another point here is that you see that crustal structures can be followed from the surface all the way down to the moor and even sometimes in the lithosphere. So crustal structures are representative of lithospheric scale structures. And the same is shown here. This we're going to challenge. It's not going to please geophysicists, no, but we're going to, yeah. Okay. I don't think we need to be go much further with that. I also want to illustrate here that there is a long history. So after saying that there's a long history of tectonic accretion along that convergent plate boundary, there's also a long history of magmatism and arc magmatism. Arc magmatism being related to subduction. So it goes all the way to 530 million years. And there's a migration from north to south. The oldest is there, and it gets younger and younger. And the latest one is the Trans-Himalayan or Ladakh batholith here, but the Trans-Himalayan batholith, its extension to the east. And that's the last events. That's Dipek is working on that. It's 55, 40 million years, and that's the last magmatic event on that, which is north of the Indus-Sangpo suture. Yeah, so construction of this orogeny belt is not just the last 50 million years. It's a long history. It's not just the last collision between India and Eurasia. There has been several blocks in between and several continental oceanic sutures. In terms of geophysics, so we have here the Tibet plateau, the Himalayas, India, and that's the Bouguer gravity anomaly. So basically gives us the size of the thickness of the crust. So these are the data in the black dots, and the model here with only isostasy. So isostasy, it's like each vertical column is independent from the neighbors, right? So if I walk, well, the ground should go down, right? Because each individual column is independent from its neighbors. That's very idealistic, right? There is some strength, and we are working on a plate, which is not just vertical columns that I can move relative to each other. So there is some flexural rigidity to that plate. But the isostatic model, the red, is not that bad. No? It gives you the first order, especially in the zone of the plateau. It gives you the first order signature of the thickness of the crust. But especially on the foreland, on both sides, there is a need to take into account that flexural rigidity. And it's in the place where the plate bends. Then you need to take that, in order to account for that curvature, you need to take into account the rigidity of the plate. And that's for about, let's say, 150 kilometers. So, in other words, it's important to take that into account, the flexural rigidity of the plate, for wedges that are less than 200 kilometers wide. For belts that are wider than that, then it's pretty much isostatic compensation. So these are the view from receiver functions. I'm not going to go through the methods, but it allows you to identify in another way, check the depth of the moho. And it confirms that it's between 50 and 60 kilometers. And the moho is flat. Moho is flat beneath Tibet. That's an important point. And you also see that there are flat geophysical structures. And these corresponds to P versus S waves conversion. So it means that the material, the rocks underneath, they will propagate faster or slower the seismic waves. And these look like they are horizontal. So you see some obliquity here at the front, but then beneath Tibet, it's all horizontal. You don't see such things. You see it here at the front, but as soon as you reach Tibet, pretty much everything is flat, according to geophysics. So you don't see these structures that go all the way down from surface to the lithosphere. Again, except here, at the front. So in terms of lithospheric scale, again, so I had one person asking me, but she's not here yet. Yesterday, and she said, okay, from the seismic tomography, it was proposed that the slab here was overturned. Wouldn't it be simpler to have a slab subducting towards the south? Fine. Nobody has been there, right? Nobody was there 50 million years ago. And that makes perfect sense. So that's where I think that was a very good example of a person that was able to take a step out of the way of the mainstream. Because our ideas about India, Himalaya, Eurasia was very much controlled by the previous work. And everybody was saying subduction towards the north, but maybe that's not the simplest way to explain the tomography. And being researcher, a scientific researcher, is also has to do with your ability to build confidence in what you see and what you think. And it's also about your ability to step aside from the mainstream. You can reproduce, and most of us reproduce all our career long, reproduce the work of others, and that's fine. And we need that to grow a corpus of knowledge. But at some point, if we want to move a bit forward, we need to have people that take a step aside.
Wouldn't it contradict with the fact that the Indian lithosphere is much more rigid than the Eurasian?
Yeah. No, that's well. To be honest, I think these images are difficult to interpret. And look at it. It's plus or minus 0.5% speed difference, velocity difference. That's not very much. And what I explained to that person yesterday, she's not here, I don't think so. No. Is that the problem here with seismic wave propagation? So you compare the time of arrival of seismic waves with the time of arrival that is predicted by a 1D model. And all these squares here are cells. And the problem here is that it's the place on Earth where the crust is thickened. And the waves are going across that crust. So we do not get the waves directly from the mantle to the surface. We have to go, they go through the crust. So it's not like I see you now. In between us, there is a crust. So I don't see you very well. And the thicker the crust, the more difficult it is to see what is underneath. So I think that's the problem here. And it looks like from the last 10 years, the seismic tomography is not making much improvement. We put a lot of hope into that, but you see that the resolution is not that great. So it was an important step forward, but now I think we're in a dead end with that. We need to develop other techniques to better retrieve the structures at depth. So let's take it as is for now. Especially it looks like here, you see the white dots, that's the Benioff plain, Modati Benioff. Looks like it's dipping towards the south. So I think there's something to it. Reconstruction, so let's take it back to 290 million years with Low Russia, Siberia, so there's no Tibet yet. And India is connected to Gondwana at that time, and terrains are going to move from Gondwana through the Paleotethys subduction and then being accreted to Low Russia, Siberia. That's the South China Craton and the Indonesian Craton. So that's terrain starts to depart from, separate from Pangaea with the subduction of Paleotethys, opening Neotethys. Boom, that's it. It's been accreted. And then India is separated from Africa. And then this will result in subduction of Neotethys. And you see here there is India, but there's also Greater India. And we talked about that yesterday. And the Indian Craton is here, that's the rigid part. But ahead of it, there is a Pan-African crust with at least 480 million years old rocks that formed here in an extended margin after the Pan-African orogeny. But this has now disappeared. And really, we don't really know the size of that because it's disappeared. And again, the current day displacement is remarkably consistent with the long-term displacement of India relative to Eurasia, which is a south to north motion. Today we see the same. So now we're going to go through the geology. And what I found also interesting when looking at, so I've never been there myself. I've only been in the eastern side. I'll tell you about that in the last two slides, on the eastern side of the Tibet Plateau, and you'll see why afterwards. So I just rely on literature. But it looks like from the literature, people, geologists, mostly focused on the Himalaya. And Tibet is not interesting. It's not interesting, it's flat, it's dull, right? Himalaya is for real geologists, the ones that are going with hiking mountains and So at some point you think, okay, how much is about the performance of doing geology in high altitude and how much is about resolving problems? So the map, just show Himalayas. Tibet we don't understand. India, we don't care. But it's very representative of the state of mind of these persons. Okay, whatever. So we have here the main frontal thrust, the main central thrust with the high Himalayan crystalline nappe, and we're going to go through that later on. And then in blue, Tethyan sediments. So that these are the sediments that were in between India and Eurasia on the margins of the continent that have been deformed during convergence along the convergent plate boundaries. We see that north of that Tethyan sediments, there is a dome structure, and we see an example of the Somorari nappe here. And then there is a suture, the Indus Songpo suture in green, and in red, the Trans-Himalayan batholith. Okay? Do you know about this geology or not so much, Sinan?
The first years are not familiar.
Okay. So we go through that. So that's the front, the foreland with the Gange basin, with river. And then it's active. So you have quaternary sediments that have been thrust over by Miocene sediments. And these are the foreland sedimentary deposits, the quartzite with pebbles and sandstones that result from erosion of the high mountain belt. And it's been deposited up front, but at the same time it's been involved in the mountain belt as it progresses. So that's here. And then as we go inland into the orogeny belt, then the thrusts start to pick up the sedimentary cover deposited on the basement. That's it. Well, here we have the Miocene, and boom, the Tertian sediments thrust over the Miocene. So that looks fairly similar to what we showed yesterday on the Western Alps, right, with the foreland and then the cover decoupled from the basement. And then as we proceed, the thrusts pick up still yet deeper and deeper units with fold and thrusts. And that has been followed all the way to the high Himalayan crystalline. And here we have the Proterozoic units, sediments that have been decoupled from the basement. And then we go into metamorphic rocks. So that's external zone, internal zone, compared to the Western Alp terminology that I gave you yesterday. And then we move to high-grade rocks, high-grade metamorphic rocks. And that boundary is the MCT. Okay, so it's metamorphic rocks on top of non-metamorphic rocks. That's consistent with the thrust. But you can also look at the structures in these rocks, and you see these schistosity and shear bands, C and S. That's consistent also with thrusting. And you can tell here that, yeah, that was enough for the geologists of the Himalayas. They stop the analysis there, right? Everything that goes to the east is not part of the story. And we have here an interesting feature that I'm going to show next. Okay, let's go across that structure of the high Himalayan crystalline. So first you have two different lithologies, orthognathis with photolith age of 480 million years, which is Ordovician, with a strong lineation. So that's representative of stretching of the rock. That's the x-axis of the strain ellipsoid, which is bare, which is on top of the foliation, and the foliation is the x-y plane, perpendicular to z, the shortening direction. That's how you reconstruct the strain ellipsoid in the field. And if you look parallel to lineation, perpendicular to the foliation, which is this plane, then you can see this CS fabric in a kyanite paragneiss, which is the other lithology of the high Himalayan crystalline. And it's also consistent with top to the north thrust. This is a nice map of all this lineation. And you see that here the turns also from north-south to east-west as the current day displacement. And this is old record. This record is probably 20 million years old, about 20 million years old. Okay, so we're looking at this unit, and it's been thrusted on top of the lesser Himalayan, the foreland, or the external zone. So now we're going to move to this place where there is a very interesting feature that was discovered about 40 years ago. The South Tibetan detachment. So you have here the high Himalayan crystalline, the thrust, the main central thrust, and on top of that, a normal fault, the South Tibetan detachment. And the resulting motion of the high Himalayan crystalline is sort of oblique extrusion in between a thrust and a normal fault. And that normal fault is also associated with localization of the pink here, which is a leucogranite. And leucogranite is here. So also, moving a bit too fast. First, I want to illustrate that here in this high Himalayan crystalline, you have kyanite-bearing rocks here, and sillimanite-bearing rocks here with leucosomes that bear garnet. So we have here everything to say that First, we have kyanite and sillimanite. You see where they stand in the PT diagram. Kyanite is on the high pressure side, and sillimanite the high temperature. So there is some alloy. So you can actually I can draw that. So it's somehow like this. Kyanite, sillimanite, andaluzite. And that's the solidus in presence of water. And if we add other, that's muscovite out, that's biotite out, and hornblende out. These are all the different solidus that can be activated during metamorphism of crustal rocks. So in other words, there might be an inverted metamorphic gradient here, with high temperature rocks on top of high pressure, lower temperature rocks. So that's an image of the local granite that sits on top of orthognaths with a protolith age of 480. Images of the migmatites of orthognaths, migmatites of paragnathes, although it's difficult to tell what the protolith is, I think. I took that photo from Roberto Weinberg, who did that work in northwest India. But I'm not fully convinced it's an orthognath. Never been there, so I don't know. And then you have these leucogranites, boudinage leucogranite, which show a top to the north sense of shear. So this leucogranite, he's recording a top to the north sense of shear, marking the South Tibetan detachment to the north. Okay, so that is, all these folded dikes, veins reflect transposition and emplacement of veins during deformation. So the most transposed ones are the earliest veins, and the veins will be emplaced and then will be sheared, and as they are sheared, they start as like this to be folded and then eventually being totally transposed. We'll see that better tomorrow morning with the Aegean example. These are leucogranite. It's not like the batholith. It's not calcaline magma with amphibole and it's you see all the brilliant spots are here muscovite, so it's an aluminum potassium-rich mica, which reflects probably a sedimentary source for the magma, so not a mantle source. Sedimentary source, crustal source. So these are the nice features that you can find with and play with the kinematics. And on top of that, you have this dike network on top of these leucogranites that are themselves, you see that's the leucogranite here. And it's been a bit pinched and swelled during deformation. And you see here the network of dikes that is better illustrated here. And the Himalayan geologist, where is he? He disappeared. Now, normally there's a red spot here. Maybe I cut the picture. Well, there is somewhere a geologist, maybe I cut for scale. No, the Himalayan geologist has to brag, has to say, okay, I was on top of the mountain, which is fine enough, it's fair enough. I'm just jealous because I never went there. And now we're going to move to that place, the dome region that is north of the South Tibetan detachment. And there you see it, so in between you have the Tessian sediments that are folded, refolded. There we can still manage to identify the bedding, so metamorphic grade is less. Huh? So it's also consistent with the idea that this structure is a normal fault. It juxtaposes high-grade rocks that are coming from underneath, being exhumed, on, next to low-grade rocks. So that's consistent with exhumation. So when you do these kinematics, rely both on structures and PT path. So that's the map of this region, and you see the Tethyan sediments, and then below that, there is a nappe of high-grade rocks, the Tsomorari nappe, and then the suture with the contact with the suture with the ophiolite, and then the Trans-Himalayan batholith, this one. And it appears here, we were discussing that yesterday, on this paper they inferred that here it's also normal fault, which is consistent with higher grade and juxtaposed to low grade. So we need to check again this paper, if it's well described or not. So this nappe, and Malika is going to expand on that, has recorded high pressure, low temperature metamorphism, eclogite facies, and even ultra-high pressure, which is identified by the presence of coesite. Coesite is the quartz stable at ultra-high pressure, beyond 2 gigapascal, which means burial down to 100 kilometers. Maybe I'll take just a short break here to discuss that conversion between mineral paragenesis, pressure, and depth. See that? There are two steps there. How is it reliable? Well, basically, what we say is that mineral reactions will record pressure, which is the weight of the rock column. Well, mechanics people, they tell us, we can have differential stress, and maybe what you're measuring is not only pressure, which is isotropic. Maybe you're measuring also the differential stress, sigma 1 minus sigma 3. And in some cases, it might be significant. So at first, petrologists said, no, we don't want to look at that because it's going to ruin our tool. No, we have a nice tool to go from minerals to pressure to depth. We don't want to look at the mechanics people because they're going to ruin our tool. I think it's too bad because what you could do as petrologist, is to gain both the pressure and the differential stress. How to do that? Take samples in different structural positions. If you have a fold, in a fold you have inside of the fold and outside of the fold. Where should be the differential stress, the maximum? Inside or outside? Inside. Check if you have same mineral paragenesis inside and outside. Nobody has done that yet, so it's a future PhD. Same with boudinaged structures. Where do you expect to have the least pressure? In between the boudins or on the sides of the boudins? In between. So sample minerals in between the boudin's neck, and on the sides. Check if they are the same. Your reference frame is the structure, gives you a time frame, and then the pressure frame will be the minerals. If they are the same pressure, then, okay, we can use pressure as a scale for depth. If not, maybe you can have both pressure, depth, and differential stress. It's okay? So let's say we have pressure. If this is the case, then we can also date minerals that we think are associated with the mineral paragenesis. This is also tricky. I'm not going to expand on that too much now. But people that have done that say, okay, the peak pressure corresponds to mineral dated at 53 million years. And then there is a decompression, fairly isothermal, down to 50 million years, 47, and then 40 million years. And this retrogression is recorded by eclogite and blue schist. And also here you can also look at the structures and sample relative to the structures. Well, usually these are not recorded in the same rocks. These would be mostly the mafic rocks, recorded the eclogite, and blue schist in the metasediments. And so in your sampling, that's for you, try to also check for different lithologic units that will tell you different parts of the story. And rely on structure for the relative timing. And then check with absolute timing. But we'll do that better with the Aegean example. And then in some places, they are on top superimposed, but below structurally, superimposed on the high pressure, low temperature, there is some hint of an increase in temperature. You see, not all the rocks follow that path. Some go like this, increase in temperature. And that's dated for this region around 13, 40 million years. And that's this arrow here. It corresponds to here. And this high temperature corresponds to domes, structural domes. Here the example of the Panma dome. But also metamorphic domes that are underlined or delineated by, so it's difficult to read here, but by metamorphic isogrades. That's a map. All these dotted lines are isogrades with the high temperature in the center, and then it moves down temperature centrifugally. So these are domes, structural domes, with high temperature rocks in the middle and lower temperature rocks on side. And the Tsomorari nap, if I'm correct, is on top of that. Is on top of that. So the high pressure, high temperature, mid pressure, high temperature. That's another example with here the mineral paleogenesis, K feldspar, garnet, biotite, sillimanite, nice prismatic sillimanite, and it goes all the way to these conditions, more than 700 degrees. And it's been dated at 6 million years for this particular example. There's also the same type of things to the east of the Himalayas in the Kangma, and all these are small domes. These. Same thing, gneisses in the core, metasediments in the rim, and isogrades that are concentric, with high temperature in the middle, lower temperature on the side, and it's fairly mid-pressure, not high pressure. Okay, that's for the dome region, and on top of the dome, there are these Tethyan sediments, Tethys Himalaya, with folded trias, the bedding. Here, well, that's a typical Himalayan geologist, with recumbent folds. And that's reproduced in that section here. That big fold here is this one. And you see, okay, so this can be reconstructed as probably as much in detail as in the Alps. There hasn't been so many geologists in this area as in the Alps, but the first order structure I think is fairly easy. If you accept the climbing, it's easy to reconstruct. So that's the South Tibetan detachment. And on top, you see that there is also shearing top to the north of the folds are consistent with shearing of top to the north. So it's also consistent with the South Tibetan detachment. Other examples of that in the Flysch or the Turbidite, Cretaceous, the Jurassic. Well, that's probably this part. And then the suture with the mantle rocks, Harzbergite, pillow basalts for the crust. Okay, so Malika is probably going to say, well, but it was Nitin. I was going to talk about that, Nitin. So I'm not going to expand, but that corresponds to the green line here. So that's really the oceanic crust and part of its mantle that has been trapped in between the continents. And then the batholith, the red part, granodiorite, diorite, enclaves, dated at 55 million years. That's the field area of Dipek. And then we enter the Tibetan plateau. Well, no wonder geologists didn't want to work on that place. So It's good for quaternarists. Flat-lying lacustrine sediments, flat. You see the Himalaya in the back. So not much is happening there. Are you not shocked by that? We're in a place where, India just hit a big punch in Eurasia. And you have flat-lying lake sediments. They might be very recent, but still. There it's just eroding. Glacial deposits, aeolian deposits, fluvial deposits, rivers, just redistributing a bit the material at the surface. No hint of big-scale deformation. We'll come back to that. So let's go now through the different models. So the first one I mentioned is the wedge model that didn't consider Tibet as part of the picture. So in this model, at that time, the South Tibetan detachment had been recognized, so the idea was that material would come in the orogenic belt with decoupled from the basement, then would be buried and then exhumed essentially by erosion, with material point moving down and up according to erosion, and with some motion here of this along the South Tibetan detachment that would at some point here at depth meet the main central thrust and the main frontal thrust. So that's the wedge theory. And the other underlying idea here that there is an equilibrium between plate tectonic force and gravity. That's the shovel. And at some point, so at first, the wedge goes like this, goes like that. At some point, it reaches an equilibrium between gravity and plate tectonics. And it's also associated with redistribution of material by erosion. But you don't need to care about what's happening to the east in that model. Everything to the east is rigid, which somehow matches the fact that there is no deformation. This one, and it also explains the inverted metamorphism with high-grade rocks on top of low-grade ones. And this is illustrated in that model where high-grade rocks would go on top of low-grade ones, causing an inverted thermal gradient, which then is reflected by the inverted metamorphic gradient. And the metamorphic gradient is the fossil isothermal gradient, inverted thermal gradient. Well, in this model, there's a gate that is open here. Here you see the South Tibetan detachment doesn't reach the MCT. It's not clear what's happening, but it'll say, okay, maybe it's not that simple. So now let's take into account, because this model does not account for the Tsomorari. Because in this type of model, the rocks go down to, let's say, at most 50 kilometers crust. That's the thickest, or maybe we can go down to 70. That's not the case, what is represented here, but as the crust beneath Himalayas is about 70 kilometers depth, right? We can imagine that crustal rocks could go down there and go up, down to 70, but not more. So how do we get rocks that went to 100 kilometers, the Tsomorari rocks? This doesn't account for that. So people move to other type of models, the ones that I showed you yesterday, the Shemenda model, where rocks can be dragged with the lithospheric mantle down to 100 kilometers, mantle depth, and then decouple, move back to the surface. And that's represented here in that section of EPA and Steck 2008, where the Tsomorari went down to 100 kilometers and went up So it changes scale, huh? Go from 50 to 100. So now I'm going to change a bit the angle of view, and we're going to look at what this high crystalline, high-grade naps is made of. So it's made of mostly of mingmatites. I just showed you that before. Mingmatites and glucogranites are dated at 20 million years. These ones. The high temperature, low pressure, mid to low pressure rocks beneath the Somorari high pressure rocks are dated here between 10 and 6, if I take all of them, which is 10 million years younger, younger than the local granites. So let's take now a step into Tibet, and that's now how we're going to see how Tibet is related to the Himalayas. It's not disconnected, from my point of view. So this was presented in 95 or 96. Myself, I was doing my PhD, and at the time I was trying, as I explained to a few of you, was trying to test whether melting of orogenic roots could promote collapse of mountain belt. And I was working on rocks that have been exhumed from that orogenic root, and are mingmatites, granites. And here this team led by Nelson that shows geophysics beneath Tibet Plateau. What do they show? So we see here the MCT, the STD, and that's the dome region here, and that's Tibet. So the Moho is here, going down, but really what is shown here are different, there are two different types of geophysical data. That's seismic reflection, so that allows to follow structures, but you see that here we lose them. So again, the structures that are identified at the surface do not go all the way down to the Moho and not even to the lithosphere. There it's the other way around. Reflectors are here concentrated at about 10 to 15 kilometers depth, this high reflectivity zone. And this high reflectivity zone matches with the zone here, in blue, these are the seismic wave. So it's seismic refraction. So here the wave are going faster, and then goes down here. See, there's up. You see that? That's a zone of low velocity. Not at the base of the lithosphere, within the crust. Within the crust, you have a low velocity zone that goes all the way almost to the Moho. The Moho is here. And you have a low velocity zone in the crust, which matches also with the high conductivity. And the top of this low velocity zone matches with the high reflectivity. So Nelson at the time, he was presenting that at the GSA meeting. I was there in the room. He said, okay, we don't agree in our team. We have geologists, geophysicists. We don't agree. Some think that these physical features reflect the presence of water at depth. Some think it's silicate melt, magma. I jumped on my chair. I said, I know what it looks like because I'm studying these rocks. I'm studying these rocks as they went exhumed back to the surface. Well, there might be some water, but it's a lot of silicate melt, that's for sure. I was really excited about that. I still have the goosebumps. And at the time, okay, some said, okay, maybe there is some melt, and that might be restricted to the zone because where they did their survey in the rift, in one of these rifts. So people said, oh, maybe there's some decompression melting just beneath the rift, but that's it. Well, if you look at the attenuation of seismic waves, that's the red part here, it's pretty much throughout the Tibetan plateau and all the way to the eastern side. So I think that's not something very limited to the rift, it's something that is big. So that's our representation, but we pretty much followed the proposition of Nelson at the time, which shows here that all this zone of low velocity, high reflectivity corresponds to a partially molten zone. is today partially molten, on top of which there might be concentration of glucogranites, magma. And how does that relate to this? Migmatites, glucogranite, 20 million years. Migmatites, granite, 10 million years. Partially molten rocks, magmas, today. That's exciting, no? I mean, and what does this mean? It means that the same process that we see here on rocks at the surface, now at the surface, probably was active there 20 million years ago. And 20 million years is the time at which these rocks crossed the solidus. They crystallized. So the first one to crystallize are now here. The second one, or the ones after, are in this dome region at 10 million years. If we wait another 10 million years, probably another dome here. Lateral flow of a partially molten orogenic root changes totally the perspective of understanding of orogenic processes. Right? So that means that you cannot restrict yourself to the understanding of the Himalayas. You have to take into account the full picture. What happens here? So that's the remaining questions. I'm not quite confident about that. Is where does this material come from? Because it's thick crust here. What are the solutions? It might come from the downgoing plate, if we accept subduction towards the north. So material that has been buried, forming high pressure naps, and then flow laterally on every side, or on each side. Maybe we can invoke a southward subduction. Maybe we can invoke part of the Indian crust, or sorry, the Eurasian crust that has been shortened, but that's not consistent with the no deformation on top. Looks like it's been thickened from underneath the carpet, and the carpet has just been uplifted. So lateral extrusion so what is the main driving force here? It's not tectonics, not plate tectonics. It's gravity-driven flow of partially molten crust, coastal route. And during that process, segregation of melt to form plutonic magmas that are going to form plutons on top. Okay, Malika, can it take another 5 minutes, 5-10 minutes?
Yeah, 5 minutes.
Yeah, okay. So, in order to test that idea, we designed a project with Julia de Sigoyer, who was also working on the Somorari at the time. And we said, okay, if that partially molten crust has exhumed in the southern edge of the Tibetan plateau, is it possible that it also exhumes other places? So we said, okay, we're going to look at this place. Maybe the cream is coming out there too. Right? And we built up a project that was twofold, was long-term behavior of orogenic roots with structure, petrology, geochronology. So that was our team. And the other team was short-term deformation of orogenic crust, looking at seismic data and GPS data. And at the time, so we designed the projects, it was in 2002, 2003. The main motivating question is, why isn't there any earthquake there? Because there hadn't been any earthquake since historical times. Although the motion in between the Longmen-shan, that's the Longmen-shan, that's the Sichuan Basin with South China Craton. And there's a motion recorded by GPS between here and there, and so it's fast moving here, and there's no motion here. So obviously there's something happening, and there's something blocking here. Well, 2008, 7.9 earthquake. We had the answer. So the geophysics team had their answer. Why isn't there any earthquake? Well, it was just a matter of time. We just had to wait for 4 years. And it's been recurring, right? There's been recurrent earthquakes in this area. So what about us, the geologists? Well, so that earthquake is related to also a jump in the Moro from 40 kilometers to 63 kilometers. So basically, that's the crust that is thickened in this area and is currently thickening by thrusting at the front. Is it related to the Pacific? Or is it related to flow of that crust from north, that has been shortened on north-south direction and then flow eastward? We were really disappointed. We went into the Tsongpan Ganze, this area where you have high-grade rocks in purple, everything dated at around 200, 220 million years, nothing around Cenozoic. Well, that's also, you have to learn, when you do research, that's not everything work as planned. So then you have to, so you build a very nice story, to get the funding. And then the work that you have to do is, well, the result is not answering the question I asked. So you need to find which question you have answered. Which is, it may seem a bit strange, but that's very often the case, especially for researchers like me. I'm very model-oriented, but I accept when the model is not confirmed that to find another model. And this is the work that you have to do, is to accept that, okay, you put your old model in the bin and you have to build another one. So we built another one with a story at 200 million years. What was nice is that with the thermochronology, so the temperature time evolution, so much of the history happened before 200 million years, but there is still a bit of a hint here, starting by a sort of a increase in temperature and then cooling, a last cooling from 400 to 0 degree during end of Mesozoic and Cenozoic. So that's during Himalayas, Tibet formation. Okay, what could that mean? So that cooling, these rocks that are today at the surface were at 400 degrees 60 million years ago. So that means that the isotherm 400 degree has been, the rocks that were there, has been exhumed to the surface. So there has been some uplift and exhumation. And they do not show much structures. A few faults, but nothing comparable to the amount of convergence and thickening that you observe in the Tibet plateau that goes from 30 kilometers to 60 kilometers. So you need to see structures that account for shortening of 100%, which you don't see. You see only faults that might account for 10% of shortening. So I think most of the thickening here happens by underneath the carpet. And the top unit is being uplifted and then eroded, exhumed, but thickening happens beneath the carpet. And that's what is shown in this picture here, that you have, it's schematized here as a channel that flows eastward and moves up the carpet. And that was first proposed by Lee Royden, and Clark. That shows here this view from looking to the west with India, Himalaya, Tibet, and here the Sichuan basin. And they propose that here, that corresponds to a rigid block, and the lower crust is trying to flow around it, and that this pattern reflects that flow around a rigid block from underneath. I think that's marvelous, It changes the perspective. We went from, again, from continuum mechanics, rigid geology, to fluid dynamics. It's much more soft. Okay, I'll leave you with that. So next step is what happens to this plateau? That's tomorrow morning, or yes, we decide that you have your lecture and then the exam, right? And
I have my lecture tomorrow.
you have your lecture tomorrow, so the exam, or do I?
So if you only one more, that one, then the exam.
Okay, so okay, that's fine. So we start the history of what happens to the plateau. Okay.
Take a break.
Take a break.